Okay, so we'll see how that works. Hopefully it goes well. So let's go ahead and get you screen shared and rolling. Yeah, thanks for the patience there, Adolph. Okay. Hello, everyone. Welcome to VSPG. Today we're hearing from Professor Adolph Yonkee from Weber State University, talking about geochronologic and geochemical analysis of the Farmington Canyon Complex in northern Utah, implications for Proterozoic crustal evolution of western Laurentia. Okay, we're real excited to have you today. Andre, can you please introduce Adolph for us?
Sure. So it's a pleasure to introduce Adolph Yonkee from Weber State University. Adolph went for master degree at University of Wyoming, and after it spent all his time in Utah, starting with PhD, that he finished in 1989, when doing postdoc for a couple of years at University of Utah, working for geological survey of Utah for 1 or 2 years, and when starting at Weber State University. And Adolph works on a variety of topics in structural geology, in tectonics, in metamorphic petrology, but also he works on detrital zircon populations in western Laurentia, and on rocks ranging from, I guess, at least Paleoproterozoic, probably Archean, to Phanerozoic. So with this, I pass it to Adolph.
Oh, thank you for the introduction, and thanks for everyone joining in here. So I'm going to try and give you a little bit of an overview of work I've been doing with a number of students here at Weber State over the last, I guess, about 5 years. So this is the view from Ogden, looking north. Tremendous mountain front here, great exposures, a lot of great projects for students right out our back door. You can maybe see some of the cliffs of the Cambrian Tinic Formation, and underneath the Great Unconformity, is the Farmington Canyon Complex, which we'll be talking about today. Want to also acknowledge Liz Balgord, another professor here at Weber State. So it's really the two of us as a collaborative effort with students that have been working on this for the last few years. And speaking of students, we're an undergraduate program here. But we try and encourage research projects, and we've had 16 students involved in doing undergraduate projects, presenting results both at our own local meetings here at the university, as well as regional and national GSA meetings. So I really want to put a shout out for students that have done the bulk of the work, I would say. And it's just been a lot of fun working with. So the outline for today, we'll talk a little bit about the setting of the Farmington Canyon Complex, which will just be FDC in following slides. I'm going to look at crystallization ages and a little bit of settings of the meta-igneous rocks within the complex. Then we're going to look at the meta-sedimentary rocks, and in particular detrital zircon patterns that will tell us something about provenance, and broadly, crudely bracket maximum depositional ages. These rocks are highly deformed, highly metamorphosed, so we'll talk a little bit about the nature and the timing of this metamorphism. And late in this pattern, we also had leucogranites, pegmatites coming in. We'll talk a little bit about their ages. Then we'll get to trying to synthesize this together, talk about implications from the late Archean to the Paleoproterozoic. As we form, we think we're in part of the supercraton Superia, and then it's rifting apart, and then reassembly of various blocks to make southwest Laurentia. The photo here is looking up towards what's called Willard Peak. Again, the tinic formation, the Cambrian sedimentary cover here, and underneath great exposures of the Farmington Canyon Complex. We're fortunate here to have uplift along the Wasatch Fault, other active normal faults to give us some of these exposures. So again, our setting here should be familiar to folks. We're sitting here in northern Utah. We're nestled between the Wyoming Province. I see Carol Frost is here, so probably very familiar with that. What's been called the Mojave Province complex here, with a mix of Paleoproterozoic and Archean inherited components, the Wyoming Archean, and then the juvenile Yavapai Mesozoic. And just how this area here fits in is what we're going to try to find out. We've been exploring the last few years and present what we found. We're going to zoom in just a little bit closer here. So here's our Farmington Canyon Complex exposed in northern Utah, again nestled between the Archean Wyoming Province, various blocks of this complicated Mojave area, and then the juvenile Paleoproterozoic Yavapai and Mesozoic provinces off to the southeast. So there were questions on just what is the age of the Farmington Canyon? Is it Archean? Is it Proterozoic? Does it record suturing of Wyoming and the Grouse Creek? How does this all fit together? So there have been a number of prior studies going back to Hedge and others. In 1983, they did some original rubidium strontium and a little bit of neodymium work, a little bit of zircon work, and got kind of a mixed pattern of Paleoproterozoic and Archean dates. Bruce Bryant did a tremendous study of mapping the Farmington Canyon, sampling the rock types, describing the petrography, really setting the stage for subsequent studies. Mueller and others, Nelson and others did geochronologic work on certain parts of the Farmington Canyon Complex. So a couple of meta-igneous bodies were dated. There was some detrital zircon work on some of the Paragneisses and documenting this Paleoproterozoic metamorphism. So here are a couple of photos from Mueller and others showing detrital zircon ages with a number of Archean dates, perhaps going over into the Paleoproterozoic. And then the plot here showing dates for metamorphic zircon rims that are characterized by high uranium to thorium ratios is how I'll be presenting them. They're doing it as low thorium to uranium ratios. So pretty complex history. There was bits and pieces there, but nothing, I would say, systematic, covering all of the different rock types in the Farmington Canyon. And as the name says, complex, it is a complex mix of rock type. So for this study, the goal was to go out and systematically collect samples from the different rock types in the Farmington Canyon. And as mentioned, I've done work with the Utah Geological Survey mapping. And so over the years, we built on Bruce Bryant's map, and we have a better idea of characterizing the setting of these different rock types and coming up with a sampling scheme. Once we have the samples, we make thin sections, do basic petrographic characterization. Then we go and separate out the zircons. We have facilities here, Weber State students been involved in setting that up and all aspects of the separation. Then imaging with cathodoluminescence, targeting, and then doing our analysis. At this point, we're just using laser ablation ICPMS analysis. And that's in part because of the complex nature of these zircons. This is not a simple group of rocks to work in. There's multiple zones. A number of these grains have high uranium, leading to radiation damage, lead loss. So it's a complicated system. So we do the imaging, and then we've done careful spotting, targeting to do our analyses. From this, present results that will constrain dates of the igneous bodies, various types. We'll look at detrital zircon age signatures of the meta-sedimentary rocks, a little bit on metamorphic dates and metamorphic conditions, a little bit on hafnium isotopic analysis, which we're still should be getting more results this week. And that was kind of our approach here. And again, involving undergraduate students in all aspects. So here's a map of the area around Ogden, showing some of these structural features and why do we have basement exposed here. So again, I want to emphasize we have limited exposure. It's not like we can go to a shield area and go wherever we want and see relations. We have to take what we have. And so the Farmington Canyon Complex was involved in thrusting. It was along the margin of the former passive margin, and there was a step in basement. And as the severe fold thrust belt formed in the Cretaceous to early Cenozoic, it carved off slices of these basement rocks and stacked them up in the Ogden thrust and Crawford thrust system. And subsequently, these were cut by actinormal faults, the Wasatch, the East Great Salt Lake fault over here. And in the footwalls, we get this uplifted, thrust faulted basement that's been brought to the surface. And these are shown in these various purple patterns here. Within the Farmington Canyon Complex, we have some main rock types, and we'll go through each of these in order. Starting with granitic orthogneiss, and that forms some fairly large bodies. They're shown in this darker purple here, including on Antelope Island and in the northern part of the Wasatch Range. Along the margins of this orthogneiss, we have migmatitic gneiss, and then we go into Donnelly Paragneiss, which will also have lenses of schist, biotite-rich schist, metaquartzite. We also have Amphibolite bodies, both cutting the granitic bodies and within the Paragneiss, and then small, for the most part, intrusions that are late of leucogranites and pegmatites. So being a structural geologist, had to throw in a cross section here. So that's the setting here, and this shows the green dots, some of our sample locations. We've worked both in the northern part of the Wasatch Range, down in more southern exposures, and also on Antelope Island, and have sampled all of these different rock types now. So the most widespread rock type on Antelope Island and in the northern Wasatch Range is this orthogneiss, and exposure here tends to make blocky outcrops, pretty massive, but it is foliated. It's typical granite in terms of subequal amounts of quartz, K-feldspar, and plage. The mafic mineral is mostly hornblende, although occasionally we preserve pyroxene. As we'll see in a little bit, it has a A-type geochemical signature, including being iron-rich and potassium-rich. Just a couple of photomicrographs of what that looks like. This is about 2 millimeters across the bottom, so cross polars uncrossed, and you can see subequal amounts of quartz, K-feldspar, and the plage, which tend to be slightly altered, and then hornblende. So getting into some of the geochronology, this is the result for one of the samples in the northern Wasatch Range. Concordant grains here give a date of 2440 MA, but note that there are a number of grains that lie off of Concordia due to lead loss. And when we look at a plot of that, we can see that the increase in discordance correlates with an increase in effective uranium content. We think much of that lead loss happened during the severe thrusting in the Cretaceous. You can try and do a crude lower intercept on these, and you get sometime in the Mesozoic. So again, grains that have more than roughly 500 parts per million effective uranium typically show some amount of lead loss, and that's one of the challenges here. Just a couple of other samples, and again, we've dated 4 plutonic bodies so far of the granitic orthogneiss, both on Antelope Island and in the Wasatch Range, and they're very consistent. This is one near Ogden that fortunately had grains that were mostly low EU and almost all, concordant dates. Okay. Another one here, coming off on Antelope Island, shows more discordant dates, again correlated with those grains that have higher uranium content. But looking at the upper part of that intercept and at the concordant grains, again consistent ages for this granitic orthogneiss. A little bit of geochemistry here, and we're doing more. This kind of typical A-type signature, so-called anorogenic in terms of high potassium, high alkalis in general, high iron to magnesium ratio, and then distinctive trace elements, high zirconium, and very high deuterium and cerium. Shown here is a plot of data for Farmington Canyon in red, and a comparison to some A-type granites from Karelia in Finland. Also going into this A-type with high field strength element concentrations. Another discrimination plot here between within plate granites and so-called ocean granites, rich granites. And the ones in the Farmington Canyon, again, unusually high in yttrium, let's say. And another plot here, ternary, showing what are so-called A2 type granites, again, all of both in the Karelia and in Farmington Canyon lying in that field. So pretty distinctive geochemical signal, possibly related to plume activity, possibly related to maybe remelting of some mafic underplate. The granitic orthogneiss is migmatized in areas, particularly along its structural contacts with the Paragneiss unit. It has a very similar mineralogy as the orthogneiss, but in addition to hornblende, sometimes we get a little bit of biotite, and even in some cases, a bit of garnet. The biggest difference is, though, the abundance of felsic dikes. And some of these show selvages along the margins, mafic selvages here, consistent with the component of partial melting. Some of these also show, we think, injection of other material, felsic material, coming from partial melting of adjacent Paragneiss. And strongly foliate and strongly deformed, all of these. And the zircons are challenging in these migmatitic gneiss. So this is just one example here, right behind campus where I teach. And we see a couple of population of grains based on both their dates and also on their uranium to thorium ratios. Okay, so those grains that have low uranium to thorium, typically between a little under 1 and about 3, those are shown in the green here. And they yield the more concordant grains around the 2450 MA date. We got the label of Concordia here. This would be 2 billion, 2.5 billion point up here. So about 2.45. Some of these show evidence for lead loss down here with a little bit younger dates. And then we have this mixed group here. We tried to target what looks like metamorphic rims are new grains that have a different CL pattern compared to these cores. But in some cases, we think that based on kind of intermediate uranium to thorium values that we ablated kind of a mixed zones in there. Then rims, as well as distinct new grains, very euhedral. These have high uranium to thorium, typically 20 to 1 up to, in some cases, like 400 to 1. Okay? And they give pretty consistent dates of around 1700 MA. Again, some of these are pretty high uranium, and they will show some discordance in lead loss. You can see kind of a complex pattern here. Most of the migmatitic gneiss we think started out as these granitic bodies, 2.45 billion years old, but with a stronger resetting, stronger metamorphic overgrowth, as well as crystallizing new grains in. And we'll come back to this a little bit later and see this is also the time of metamorphism in the Paragneiss. Amphibolites, pretty standard mix of hornblende and plagioclase, oxides. Some of our amphibolites have garnet, a number of them have minor quartz. Here's a thin section, and you can see the hornblende, you can see the plage, and then we also have little bits of quartz in some of these. Amphibolite occurs in multiple settings. Not terribly large, but intermediate sized mafic bodies that show layering, plage-rich layers, almost hornblendite layers. Occurs as mafic dikes, and it might even have been basalt flows in the Paragneiss, although again, all structures obliterated by subsequent deformation and metamorphism. And as we'll see, this has been challenging to date, but we've been able to date one layered mafic body and then one larger dike having plage-rich zones in. And for those two bodies that we've been able to date so far, one of them associated with the granitic orthogneiss and with it gives a very similar date of 2450 MA. Okay, mostly concordant grains, a few discordant. These have higher EU. Just getting back results last month from a student project. There was a larger mafic body cutting a granitic orthogneiss, and this one yielded a date of 2120. Okay, and all concordant grains in that one. It was surprisingly well behaved, but at least two ages of mafic igneous activity here, one at the same time as that early granitic at 2.45, and one that's younger at 2.12 billion. The Paragneiss, beautiful rocks, variable mineralogy, mix of feldspars and quartz, and typically containing biotite and garnet. Okay, well layered. Some of these are migmatitic, and they also contain lenses of metaquartzite and biotite-rich schist. The portolithy for these were probably some combination of lithic to feldspathic wackies, and again with lenses of quartz-rich sandstone and mudstone to form the metaquartzite and schist. Here's a photomicrograph of a typical Paragneiss. Biotite here, we've got plage, quite a bit of quartz, some K feldspar. The metaquartzite, again, in with the Paragneiss. In some areas forming relatively thin packages, in other areas fairly thick packages. And these are characterized by dominantly quartz. They also have a minor biotite, minor garnet, that's shown in the photomicrograph here, just a little garnet. Also, this one has a little bit of K feldspar, and some of these quartzites have chrome mica fuchsite in them as well. and strongly deformed, well foliated. The interlayered schist, characterized by more abundant biotite, also garnet. It's going to have some quartz and feldspars. And importantly, it has sillimanite in it. Okay, maybe see a little bit of that here in the photomicrograph. It's maybe a little blurry here, some of the cross sections of the fibrous sillimanite here, garnet, biotite. In most areas of the Farmington Canyon, we lack muscovite. We're in the second sillimanite isograd, so we have a K feldspar, sillimanite, biotite, garnet, and in some areas we also have cordierite, which is interesting. We'll talk about what that says in general for pressures of metamorphism. Quite a bit of biotite in some of these. We think of mudstone totally. And most of these are also magmatitic. They've undergone partial melting. So we take these Paragneisses and metaquartzites and schist and separate out the zircons. This is a typical mount for one sample, another one here. Image them with a CL to target different zones. And you can see a range of different zircon types. You might be able to look in, and we'll look in a little more detail. Some of these grains, you can see some of them have metamorphic rims. And so we're going to analyze these to look at age patterns, tell us something about the ages of the source areas, provenance. We'll look at the youngest zircon grains to get an idea of maximum depositional age. And this is really the only way we have of possibly correlating rock types across the Farmington Canyon Complex. And we have different outcrops on Adolph Island, Wasatch Range, different thrush needs. These are highly deformed, no sedimentary structures left. So if we're going to try and make any sense at all of stratigraphy, of correlation, we're going to have to do it through these seeds. Okay. So we're going to look at 3 different types of patterns. And I want to say that we've now analyzed 16 different Paragneiss, schist, and metaquartzite samples. The Paragneiss samples, in quartz, feldspar, 10-20% biotite in most of these, started out of some sort of lithic or feldspathic wacke. Commonly show Archean grains, came from about 2.5 to 2.75 big. Okay. So these are Paragneisses in the northern part of the Wasatch Range, one's from the southern part, one's from Antelope Island. Somewhat similar patterns, but also variations between them. We see different relative amounts of this 2.45 peak here, which we think is reworked from those prior granite plutons. This one having a big spike in it. This one small, this one some of these, the Paragneiss also contain a smattering of younger butyral zircon cores in the kind of 2 to 2.3 billion year range, which bracket the maximum depositional age. So again, the Paragneiss are deposited subsequently after these granite plutons form. These younger dates in here, we'll look at hafnium isotopes in a little bit, but we think these are forming during a younger rifting basin forming event. The metaquartzites all are dominated by Archean grains, possibly from the Wyoming Province. 2.55 to 2.8 billion is the broad range. Many of these have a mode around 2.7. Some of these have older Archean grains. The oldest one we found that's concordant is about 3.9 billion, which again is possible coming from the Wyoming Province. A very limited number, but some of these 2.0 to 2.3 billion year zircon grains that again are going to bracket our maximum depositional age. But compared to the Paragneiss, dominated by an Archean plutonic source. The schist and some biotite richer gneisses and this odd garnet gneiss sample here tend to have younger grains in them. Although some have a dominance of Archean, some of them have a dominance almost entirely of Paleoproterozoic. These have been a challenge to analyze. You can see our number of grains here. I forgot to point that out on other ones. We try to target around 150 cores and 50 rims. And in some of these Paragneiss samples, we just don't get that many zircon grains that have large enough preserved cores to analyze, or we try a core and end up getting part of a rim as we ablate in. So much fewer numbers here, but a general pattern emerging that these tend to have younger zircons that are probably related to ongoing igneous activity as the basin is forming, as these sedimentary protoliths are accumulating. This garnet gneiss here was unusual in that we analyzed, I think, over 150 grains. Almost all of them ended up being discordant, and almost all of them ended up having over 500 ppm effective uranium, some of them like 5,000. So whatever the source for this was, very odd. Don't know what to make of it. So we'll put this in summary by different groups. Here's our different metaquartzites, again from north, south part of the Vortex Range, Antelope Island. We've tried to sample a number of areas, and they do have similar DZ patterns. Might mention, yeah, these are kernel density estimators here, so we're smoothing out a little bit. Smattering of younger grains, but dominated by Neo-Archean and a smattering of older Archean grains. That could be coming from the Wyoming Province. That's our interpretation now as the main provenance for those. The Paragneiss, more complex mixtures, a little bit younger in terms of the Archean, and they also include variable amounts of this 2.45 and a little bit more of these younger 2 to 2.3 billion year old grains. The schist, again, dominated mostly by these youngers with varying amounts of Archean in them. And this kind of looks like my office during finals week here, this plot, just putting them all together. So complex sequence of meta-sedimentary rock. Didn't get time to put all of the metamorphic rim data together, but here are 3 samples. This is a little bit of a close-up. You can see the cores here that we target, and then the rims. And the rims in CL are characterized by kind of a uniform dark gray pattern. And when we analyze these invariably have high uranium to thorium ratios, typically between 20 to 1 and about 400 to 1. What was a bit surprising was the range in ages of these rims. Again, have to worry that maybe we're getting a little bit mixing in with cores in some of these, but we've separated these out based on high uranium to thorium ratios to try and minimize that effect. And there's a range from almost, well, a few of the rims over 1.8 billion down to about 1.6 billion. There's some limited data on monazite from the Farmington Canyon as well. And most monazite ages are between 1.7 and 1.6 billion. Different samples appear to have different modes of metamorphic rims, with kind of a pulse closer to 1.75 billion and one to 1.65 billion. We know these rocks have undergone polyphase deformation. We have very complex fold patterns, fold interference patterns. And our preliminary idea is that we had perhaps 2 periods of peak metamorphism, protracted metamorphism, again with the ICPMS. We don't quite have the resolution. One of the things in the future is to maybe try TIMS if we can figure out how to get the rims separated. Just a little bit on conditions of metamorphism. Just so you realize, yeah, there is no stratigraphy preserved. There are isoclinal folds everywhere that are refolded. Things are migmatized in places. Prior work by Doug Barnett and others, they did a little work back in the 1990s. And if anyone is out there that's a metamorphic petrologist that wants to get involved with this, really some great rocks to do geothermal barometry on. Their estimates done back then using garnet, biotite, plage compositions are shown here, arranged for the Wasatch Range for their samples on Antelope Island. They're coming up with pressures that correspond to crustal depths somewhere between about 12 and 30 kilometers. Their estimated peak temperatures are between 650 and 750, 780 degrees C. So these are high-grade rocks. With few exceptions, we lack muscovite. Instead, we have cave feldspar silmonite in these politic lithologies, and number of lithologies, particularly the politic ones, show evidence of partial melting. And that's consistent with it, both in some small areas in the Wasatch Range as well as Antelope Island. We do pick up cordierite in places, along with garnet, which again is consistent with this kind of general, not particularly high pressure, but high temperature conditions. Okay, so intense high grade metamorphism, polyphase deformation. And so our attempts to put together stratigraphy are limited. And then the final rock type in the Farmington Canyon are these leucogranites, rich in quartz, cave feldspar plage, and practically no mafics. Late stage, little deformed. They tend to be high uranium with a lot of discordant ages. But when we do the chords and get our few concordant grains, we're getting somewhere around 1.64 to 1.68 billion. So they're coming in at the end of this deformation metamorphism, consistent with their being cross-cutting and little deformed. Just mention a little bit on hafnium isotopic signatures. We have some limited data. We were supposed to get more in March, but instrument problem, but we should be getting that here in the near future. So we're going to use hafnium isotopes to get at idea of potential sources, whether it's depleted mantle, non-depleted mantle, or crust. And we're going to use this value of epsilon hafnium, which will compare our hafnium isotopic ratios relative to chondritic uniform reservoir at the time of formation of these grains, which we'll get from uranium lead dates. And from that, we'll be able to tell, are we having sources from crust? Are we having sources juvenile, depleted mantle, or perhaps something that might even be some enriched mantle? So we'll take a quick look at that. Here's results so far. Here are Orthogneiss. Remember that came in at 2.45 billion, and they show a range from about +4 to -4. Here's one down to -6, which could indicate some combination of non-depleted mantle or to enriched mantle, or a component from older crust. We lack any xenocrystic core, so unsure on that, but preliminary thought would be that there is some amount of crustal contamination in this. These are the late leucogranites here. They're highly evolved, negative epsilon values. consistent with remelting sources from the Paragneiss and the Orthogneiss here. Here are the metamorphic rims. We got to have a little bit of hafnium isotope here, again, similar pattern. And so far, this is in green are the data from the Paragneiss detrital zircon cores. A big scatter. Okay, some of these are juvenile, came from juvenile Archean rocks, some from evolved Archean rocks that were probably reworked. This is a compilation from Garros and Pecha on some of the Canadian Shield values here. And then our younger detrital zircons, remember that 2.0 to 2.3 roughly, are a range of depleted values to somewhat enriched values. So a complicated pattern. Again, we need quite a bit more data, which we'll be getting to try and test some different ideas here. So here's the takeaway model. So 2450 MA, we have big granitic plutons. We have some moderate-sized layered mafic bodies that come in. Possibly these came into some sort of Archean crust, but we see no evidence of that preserved in our current exposures. The hafnium isotopes could suggest that. It could also be some sort of unusually enriched mantle that is the source for that. Following this early igneous event, we then had erosion and then deposition of a sedimentary sequence that included some feldspathic or lithic wackies, in this light orange, some mudstones in the yellow that are become our schist, some quartz-rich sandstones that are become the metaquartzites in green, some mafic dikes, some more layered mafic bodies. Some of these actually have ultramafic layers within them. Again, highly structurally deformed, so hard to put together the details here. But we've deposited then a supercrustal sequence over these early granite plutons and layered mafic bodies. Then we have polyphase deformation, high-grade metamorphism of our amphibolite to granulite facies, and we're going to change our granite plutons into our granitic orthogneiss, migmatite in some areas. Take our sedimentary sequence here, make it into our Paragneiss, layered Paragneiss with bits of metaquartzite and schist, and disrupt the dikes and the mafic bodies here. And then finally, towards the end of that deformation, intrude some late-stage leucogranites and pigment. Going to finish here with just a little bit of speculation, maybe. And Andre knows about this. So this comes from a recent paper by Ramon and others, where they looked at the Snowy Path supergroup on the southern part of the Wyoming Province. Impressive sedimentary sequence there. And it lies on some Archean basement, which is also the southern part of the Wyoming Province. And then there are some 2.45 billion-year-old igneous rocks. For comparison, the Huronian supergroup here, again, 2.45 billion igneous episode. Then thick sequence of sedimentary rocks. It includes quartz-rich things. It includes mudstones. It includes diamictites. And it's cut by dikes that are in these 2.1 to 2.2 billion year range. So there are some similarities to the Farmington Canyon, and that we have this 2.45 and this 2.1 to 2.2 billion year igneous events, including mafic rocks. And we have similar DZ patterns with a big input of Archean grains and a smattering of these younger, roughly syn-depositional grains. Big difference, though, is in the Farmington Canyon, things have been polydeformed and metamorphosed. We lack any stratigraphy. We don't see any things that would be diamictites, and intriguing, don't know what to make of it. We do not see any calcsilicates, any metacarbonates in the Farmington Canyon. So not perfect, but it does suggest that there is some relation of the Farmington Canyon here with these rocks along the southern part of the Wyoming province, here restored from paleomag data, back to around 2.1 billion years. Again, we'll just, this is kind of an addition onto the work that Bleecker and others have done, Ramon and others, on this idea of the supercraton Superia. And we're just adding the Farmington Canyon in here, in that we also have this 2.45 billion year igneous event, granitic plutons you can see here in multiple different areas, mafic dikes or layered mafic bodies, also of this age. Idea that is related to some plume head. If you kind of project these back, potentially we'd be near that here in the Farmington Canyon, which might explain just the tremendous amount of these granitic plutons with these A-type signatures. We also have in the Farmington Canyon this 2.1 to 2.2 billion year event. We don't know orientations of dikes or anything like that. Everything's so deformed. But again, it would fit in and be consistent with these dikes in the other area. So the kind of working model here is that we're going to become part of Superia here in northern Utah. This again has this early plume activity, and then a subsequent plume activity that leads to the final rifting and breakup part of Superia. Wyoming, Farmington Canyon is going to go their way, Superior their way, and then we're going to come back and recombine and make Southwest Laurentia, which is the final thing to end with here. So part of Superia, we're now going on our journey, and somehow we're going to end back up being bound by Yavapai Mesotzal down here, and whatever blocks make up the Mojave coming together. So just a brief comparison here. Like the Mojave province, we have intense deformation, high-grade metamorphism around 1.6 to 1.8 billion. Parts of the Mojave show evidence of an Archean input and a strong 2.45, 2.48 billion year input in the so-called Vishnu Basin. Other parts, including Death Valley area, this part locally exposed in southwest Utah, lacks that. So, but together, consistent in having this late Paleoproterozoic high-grade metamorphism and late-stage leucogranite. So we stitch things together. We also have here in Utah, Yavapai Province exposures. This is our 1.8 to 1.7 billion year old juvenile rocks coming in, also intensely deformed, and we'll stitch together then Southwest Laurentia. So Farmington Canyon has a, let's say, a complex and a very interesting history. It started almost 2.5 billion years ago. There may be older crusts around. We do not see any evidence at the surface. The hint would be in the hafnium isotopic signature. Very large outpouring of our development of silicic magma, along with mafic, a bimodal signature, perhaps plume related. Then we get deposition of a meta-sedimentary sequence. We don't know the details of it, but the maximum depositional ages put us somewhere in that mid-Paleoproterozoic. And we also have mafic dikes, perhaps flows coming in at that time. The sources for this meta-sedimentary sequence were probably varied, including potentially the Wyoming province, potentially other Archean cratons, as well as thin rifting igneous activity. And so putting this together, we're proposing that the Farmington Canyon was part of Superia, possibly located near where that 2.45 plume would have come in. And that was kind of like the 1-2 punch that then led to the breakup of Superia. Then we combined things together, intense deformation, high-grade metamorphism, which makes it a challenge, I would say, to unravel the history of the Farmington Canyon. But it's been a fun project. It's ongoing, lots of students, and we hope to continue future studies. And at that point, I'll entertain questions.
Thanks, Adolph. Great stuff. Yeah, so we'll go ahead and switch to question and discussion. You can ask questions a couple ways. You can type it and I can ask it for you, or you can find the reactions button at the bottom of your window. And at the bottom of that pop-up, once you click it, there's the raise hand, and so you could do that as well. We had a comment in the chat from earlier on. I'm sorry, I don't really know how to properly pronounce your name, but it's Easton Mai asks or says granites are similar to craton and related granitoids in the southern and Grenville provinces near Sudbury, Ontario, an area that also is linked to Karelia at around 2450 MA.
Yeah, and I think, let's see if we can go back here. And I'm not sure if that's kind of, might be some of this in here, but yeah, there's in southern Ontario, yeah, I'm not sure just on the reconstruction here, but southern part of the Superior, yeah, has those types of plutons similar to in Karelia. I don't know about the geochemistry of those. I showed a little bit of data I found on the Karelia, but I'm unsure if anyone knows of geochemical data, or we'll be looking into that for some of these other plutons. But it is interesting, that you find these similar age in multiple different blocks.
All right.
That was Mike Easton of the
Mike
Ontario.
Easton? Okay. All right, thanks. Mike Easton. All right. So nothing else in the chat. Or Carol Frost says, Adolph, great talk. At the start, you posed the question of how Grouse Creek and Wyoming might be related. Any comments?
I was hoping people forgot that. So yeah, basically I don't know that, it's been speculated that the Grouse Creek could have been connected, and then the Farmington Canyon, some of the the meta-sedimentary units here were in a basin between those two. The Grouse Creek is, I would say, even more challenging than the Farmington Canyon. So it does have an Archean record to it. It has our late Paleoproterozoic metamorphism. But then in addition, it's also was in the hinterland of the severe, and so it has a very strong Mesozoic overprint, and then the core complex extension overprint. So seeing through that is challenging, and Vince Isaacson did a thesis on that, and I think that's probably the best data available. So I had thought about putting the Grouse Creek block on here, sitting in here, and then kind of chickened out and just left it off. So I don't know if Carol has any thoughts on that.
Yeah, Carol, if you want to speak up, feel free.
No, I don't have any inspiration. I was hoping you did. Thank you.
Inspiration to go out and do more work. How about that? But it is my colleague Liz Balgord. She went out there and did a little bit of sampling to see what could come up, and it was very, very messy grains.
Hey, we don't have any more hands up or messages.
So maybe I can follow on this question. So you have a lot of 2.55 detrital zircons. which are, from what I remember, quite unusual to Wyoming and to Superia. And if I remember correctly, we are common to gross block.
Yes.
So any thoughts if it could have been derived would be interesting to do, maybe hafnium or oxygen, kind of to get more data to compare, but any thoughts on it?
Yeah, so the metaquartzites look like they have a Wyoming Province signature, whereas some of the Paragneisses, the Archean is, they include the mode of 2.55, which is in the Grouse Creek. So yeah, I don't know if hafnium isotopes been done on the Grouse Creek. Need to look into that. If not, that's something we might pursue. The other thing that we're looking at is doing, in addition, and again, we'll be getting a bunch more hafnium isotopes. That first data set there was kind of a scattered approach. We just did a more focused on different age groups, including that 2.55 a month ago. But the machine was down, unfortunately, and it should be being run this week. The other thing is potentially, and I don't know if other folks have tried this, looking at some of the trace element patterns, for comparison.
Great.
And I don't know, and maybe I'll ask Carol here if, what has been done hafnium isotope wise or trace element wise on some of the zircons in the Wyoming province.
Well, Adolph, there isn't a whole lot, but the little bit we did in the Granite Mountains suggests a Hadean parentage.
Right.
That's pretty
Yeah.
distinctive, so maybe that would be something to compare.
Yeah, and we do have some of those, 3.7 to 3.9 billion year old zircons here, which sure seem like that. It's Sakawi ice up there that have that very old component.
Yeah, it sure seems permissive, but I don't know how you prove it.
I guess what I was thinking is just things like, the more voluminous or widespread, granite, granodiorites are maybe some of like the Bighorn magmatic province. And I just didn't see any in the, but I haven't done a thorough literature review.
Yeah, I know that Paul Miller was very disappointed that he had another appointment, and he's going to watch your talk after. But he's documented little bits of leucogranite intrusion of about 2.45 billion years up north, and there's a little bit in the medicine bows. It's just an intriguing association that I really don't understand.
Yes, so if I can follow Adolph maybe to more uncertain area. So if we put Grouse Creek against Wyoming Province in Paleoproterozoic, here, and so it potentially could look like a triple junction at Farmington Creek. But if we follow it to the south in your reconstruction towards Montana meta-sedimentary terrain, it's interesting that up there are also like 2.45, 2.5 events that Paul Miller studied, and including like mafic events, but they interpreted it related to deformation, to collision. And so if you have any thoughts, or maybe if Paul Miller, maybe we invite him next year to talk like sort of how it fit together.
Yeah, I do not have thoughts on that. I guess, just aware that event is up in southwest Montana.
Yeah, I have a couple more, but maybe I let other people ask.
Yeah, Richard Ernst seemed interested in the topic. So Richard, if you wanted to speak up, you may.
There's a comment from Rob Rainbird in the chat.
Yeah, Rob Rainbird said next, correlation with the Huronian will only work if your MDAs are older than 2.2 billion, age of the Nipissing diabase. You probably need to do some follow-up ID TIMS work on your young zircon grains to establish this.
And that is, yeah, what we would like to do. And probably looking at the young grains in the Paragneiss, the schist one, yeah, the zircons are very, very messy there. And again, you know, the number of grains we have down there in the younger age is limited, but yeah, the goal is to kind of do this tandem, starting with the ICPMS and then targeting grains for TIMS, but it's going to be a challenge because many of these grains have rims, you know, so we have some young cores, but if you have the metamorphic rim, it's something we want to do, but I don't think it will be easy, but that's a good point.
And do you have any response, Richard Ernst asked that if there are 2.45 granites in Grouse Creek block? I don't remember any, but
no, yeah, there's been nothing. There's 2.55, but yeah, none of the 2.45, and I don't think geochemically it's, you know, it's like what we have here.
Can I just comment maybe? I don't know how my internet might be very good, so I may be breaking up here, but yeah, we might expect, you know, that kind of melting of lower crust to produce, you know, A-type granites or granites in association with the plume might be kind of closer to the plume center. So, but if you put the Grouse Creek in that little notch there, that would put it close. Yeah, no, I'm really intrigued by this discovery of this sort of silicic, this granite province now that is much enlarging what we have already kind of recognized a bit in the as Mike Easton was saying, in the southern Superior. So the great Metachwan event, plume event, seems to be getting larger. So neat stuff from my perspective.
Any thoughts on geochemical signatures that we should be looking for?
No, because it depends so much on presumably on the lower crustal rocks that are being melted. In some cases, it could be, you know, underplate produced by the plume itself, partial melting that accumulates in the lower crust, and that could then subsequently be melted by additional heat from the plume. And so there should be some geochemical similarities then to the mafic ultramafic rocks of the plume of the lip itself, but then other rocks partially melting would have a totally different earlier history, and so there wouldn't be any geochemical connection in those cases. Be interesting to compare yours with the Crichton granite, which is near the Huronian, and just to see whether the geochemistry in that particular case, and maybe some of the other ones that Mike mentioned, just to see if the geochemistry of these A-type 2.45 granites is sort of homogeneous over that sort of distance. There's a second, the interesting thing is, I just mentioned there's an earlier pulse of this event at 2480 that includes, you know, that includes a subswarm of dikes in the Metachwan event, plus the blue draw intrusion in the Wyoming craton. So there's a kind of, and some new dikes called the Elbow Creek dikes. So there's a 2.48 pulse as well. There's also a really dominant 2.60 pulse, 5.9 pulse in the Metachwan dikes. So, you know, in terms of kind of pulses that could be part of the story, sure, there's a 2.45 pulse, but then there's also potentially two older pulses, a 2.59 and a 2.80-ish pulse that could be part of the broader story.
Right. We don't have anything in the chat or any hands, so I'll just leave it open for open discussion. And if it's quiet enough, we'll call it. All right, thanks, Adolph. That was great. A good discussion at the end. Really cool contribution to the series, and it was really great to have you on.
Thanks everyone for all the different times zones to join in.
Mike Easton threw something out there if we want to keep it up. It's a long one. He says, problem with correlation of detrital population with the Huronian will also have to account for likely slightly different Archean source terrains. Plus, there are differences with the Huronian stratigraphy. Geon 26 population dominant below Ramsey Formation, Geon 26 in higher units. Not that the Huronian is also cut by 2258 more mafic intrusions. Becker et al. 23. What you present is somewhat Huronian-like, but also different. Also, we have 2086 million-year-old mafic magnetism plus the marathon dikes, 2125 to 2105 million years. He apologizes for internet connection. So he's sending this here. So if you want to discuss, this is an open platform, or you guys can chat about it over email, I guess.
I guess he doesn't have good internet, so he sent his email if you want to get in touch with him.
Okay, yeah, that would.
All right, so we can link you this, and Mike, you guys can connect over email. But yeah, Adolph, thanks again. Thanks everybody for being here.
Oh, maybe just 2 quick questions.
Oh, sure.
As I presume you don't have any structural information, but any ideas about versions of deformation at 2.6, 2.7? Is it all coming related to Mojave and Yavapai, or any indication that anything happening between Grouse Creek, sort of any east-west directed deformation kind of?
I would say we have a lot of structural data and I cannot make any sense of it.
Okay.
And part of the issue is that, we have isolated exposures. All I can say is it's a complicated polyphase.
Okay, and the last quick question, you showed it looked like 2 series of thrust, like one at the top related to severe orogeny, and when you had Ogden thrust or basal thrust, what is it also related to severe orogeny, or it's previous
No, that's all severe. So
okay.
Yeah, and we're just stacking those thrusts up.
Mm-hmm. Okay, thank you.
All right. Well, everyone, take care. We'll see you next week.
Thanks.
Right. Bye.
Bye.
See you, Adolph.
Mm-hmm.